Hi, welcome to Business Mathematics. Today we are going to talk about annuities. Annuities are regular payments with a fixed rate of interest. So here I have attempted to draw for you the situation. Uh, these are year 1, 2, 3, 4, 5. Suppose we are organizing an annuity where we are going to make a quarterly payment into a certain account. So quarter 1, 2, 3, 4 we pay, and second year again we pay, third year, fourth year, fifth year, and so on. Suppose we have a fixed rate of interest. We want to know future value of our money at the time of the very last deposit, how much would be in that account. This is a financial instrument for saving money for certain time in the future, or similarly could be like the installment payments for certain purchases you make or mortgages and such. The idea is rather similar. Let's go ahead and practice this. Suppose we are preparing for a certain future expense. We are going to go ahead and make a payment that is the regular payment we are making every period. Suppose that payment is say $500. We are making the payments 4 times a year, so that means our arrangement is a quarterly arrangement. We are going to make the payment for 5 years, so T is 5, and rate of interest that hopefully we get from certain bank is say 8%. Remember, we write it as 0.08. The question is, how much would this thing generate for us in the future? So that's the future value of this amount is equal to the payment. So that's going to be $500 times the fraction is 1 plus the rate of interest, which is 0.08, divided by the number of compounding we have every year, so that's 4. This is raised to the power of number of compounding that we are going to do. So 4 times 5 years, so it's going to be 20 of them. We have to subtract a 1 here and divide by this fraction again, so 0.08 divided by 4. You might want to calculate this little by little and make sure everything is correct to as many decimal places as your calculator shows, and then do the final calculation. So this becomes 1.02, this parenthesis 1.02 to the power of 20 minus 1 divided by this parenthesis again is 20, excuse me, 0.02. Let's go ahead and use our calculator to find out what this is. So we calculate this thing and it turns out to be $12,148.68. Okay, how much did we actually pay into this program? Every quarter we were paying $500. There were 20 payments, and the total payment we have paid into the account is $10,000. What did we get out of it? Thanks to the interest, we are getting $2,148 extra back. So the total interest accumulated during this time is this amount. So this is the idea of annuity. So your regular payment into a certain account under a fixed interest, compounded in in the scheme that comes up, and we calculate the total amount by this formula. Now you might be wondering, where does this formula itself come from? So I'm going to spend the rest of this time explaining that formula. It has something to do that you have actually seen in algebra, uh, perhaps in high school, and this is something referred to as geometric series. The idea is, well, you're making a payment there, and that payment accumulates for all this time, and then the next payment, it's going to accumulate one less time, and next payment one less time, and so on. And then you're adding all these things up. Accumulation every time, it has to do with the interest that you are collecting, and when you write it down, it all turns out to be an example of a so-called geometric series. So let me go ahead. This is an optional part. All you need to do for your problems is to apply that formula. Remember, this is future value, this payment, and to get started, see where does this formula come from. Let me bring you back to something from high school. You probably see this quite often: x minus y times x plus y. What is this? Well, if you remember from high school, when you multiply them, minus yx and plus xy cancel each other out, and you get this nice little identity. X minus y times x plus y is x squared minus y squared. Now there's a whole family of these things, not only for power 2, but just about every power has one of these things. This term is going to be fixed in all of them. This one is going to start expanding and collecting more. Let's see what's the next one. It's possible that you have seen in high school too, in your Algebra 1 class. You might have come across the following: x squared plus xy plus y squared. Perhaps you have forgotten this thing. Let's go ahead and practice what happens. X times x squared becomes x cubed, times the next one is x squared y. Next one becomes x plus plus x y squared. Now y times this, y times x squared. So let me write it like here: minus y times x squared. Y times xy is minus xy squared. Y times y cubed is minus y cubed. Notice that these two cancel, and out comes something interesting: x cubed minus y cubed. Let's see what is the mystery here. X squared, then x to the power of 1, and then there is no x or x to the power of 0. Y goes in the opposite order. There's no y here, which means you can write it as y to the power of 0. Let me write this. It is x squared y0. This is x1 y1, and this is x0 y2. X to the power of 0, y to the power of 0, that's just 1, which we don't write, and power 1 is just that variable itself. Now we see the pattern. Powers of x goes down from 2 to 1 to 0. Power of y goes from 0 to 1 to 2, and so on. Can you guess what the next identity of this type is going to be? It's x minus y times, what do you think we are going to start with? This is the pattern that is easy to follow. It has to be x3y0. Now x's go down, y's go up. So x2y1, x1y2, and x0y3. In a more conventional way, we write it like this: x2y plus xy squared plus y cubed. That's the normal traditional way of writing this. Well, when I take x and multiply by all of these things, let me write the x first. So x to the power of 4 plus x3y plus x2y2 plus xy3. I multiply y by all of these things and write the y on the second entry. So it's going to be minus times this one, x3y, times this one is going to be x2y2, times this one, xy3, and times the last one is minus y cubed. You notice that these cancel, magically cancel. We have a so-called telescoping cancellation, and out comes what? Out comes x to the power of 4 minus y to the power of 4. Let's do one more of these things just for good measure. What do you think is the next one going to be? You want to pause this thing and write it all by yourself, so you got the hang of how this one goes. Is that right? What does it start with? x4. Then x loses a power, y gains it. X loses a power, y gains it. X loses a power, y gains it. And x completely loses everything, and now y. Final effect is that when you multiply all of these things and simplify after this telescoping summation, what you get is x to the power of 5 minus y to the power of 5. Okay, so in general, we see that if I'm adding this particular sum, I can write it in an interesting way. If I have something like x to the power of 4, x3y, x2y2, xy3, and then y4, I can take this, divide it by that term, and that is going to be my shorthand for all of this. Before we go any further, again, let me remind you, it's optional material trying to explain where does that formula come from. The formula looks a bit intimidating, and you might be wondering, well, where did this thing come from? This formula, where does it come from? Again, we are trying to calculate a bunch of future values and add them all together, and in the addition of these things, each of these present future values are going to have a different exponent because they are being compounded for different number of times, and it's going to be very similar to the situation that we have here, that you have these powers. You notice you have 4, 3, 2, 1, and finally 0. We have something similar to that. To make the matter simpler for us, let's take y to be 1, so that our problem looks a little bit less crowded. So what does that look like? X to the power of 4, x cubed plus x squared plus x plus 1. Now this is rather easy to remember. X to the power of 5 minus 1 over x minus 1. So instead of y, I put everywhere 1, because in the formula that we need, 1 will do. We don't need anything else. Just as a matter of practice, let me ask you the following. If I ask you what is x to the power of 19, x to the power of 18, x to the power of 17, well, we are going to get tired of writing all of them. So we kind of abbreviate the situation and just write beginning and end, and put this ellipsis triple point here, indicating the reasonable pattern that you see between these two that keeps going. Well, here are 20 terms to add. Is there a shortcut to doing this addition other than just really finding all of these things and add them up? Well, yes, it happens to be x to the power of 1 exponent larger than this, 20 minus 1, and then x minus 1. Expressions like this are referred to as geometric series. Geometric series is a type of mathematical entity you see that in calculus, but it so happens to be behind all interest rate calculations that use the fixed interest. So things like installment payments, mortgages, annuities, and such All of these cases revolve around an application of geometric series. So we have the formula for geometric series here. Now the question is, where does this come from? If you go back to this situation here, the payment that we pay here, it's gonna go through certain number of compoundings. There are 20 periods total here, but it starts compounding here, 1, 2, 3, and this is going to be case 19 here. You've lost 1 from the beginning, so it becomes x to the power of 19. The payment that is going to be paid on this end of the second month, that's going to go through 18 compounding to the end. The third one is going to go through 17, and fourth one 16, and so on. And the very last one, well, there's no compounding at this very last one. The situation turns out to be just like this, like x to the power of 19, x to the power of 18, and so on, until very last one, which is 1. So you remember our formula for accrued amount was the payment times 1 plus interest rate divided by n to the power of nt. So we are making the same payment in each installment. However installment plan you have chosen is the same payment. And then we have 1 plus interest rate in all of them is a fixed r over n. Now we take this for a certain number of payments that we are going to make. We are going to write for a problem like this. Remember, the very first payment is going to go through 19 compounding. So I'm going to compound it for nt minus 1, and the next one is principal times 1 plus r over n times, that one is going to be 1 less compounding, and so on down the road I go, all the way to the last principal that we pay on the last day of this contract. This one, you pay that principal p, and well, there's no compounding to do here. It's just whatever you paid, that's what is going to sit in your account. So I factor the p out, and then, just like how we learned here, we have to take our exponent, increase it by 1, so I'll have 1 plus r over n. Whatever the exponent here is going to be increased by 1 nt. Then I have to subtract the 1 from it, divided by what the x that's showing up here is just the 1 plus r over n. That is the x in our problem. And then I have to subtract the 1 from it, minus 1. So P, which stands for that payment that you are making monthly or in each compounding period, times this expression, which is interest rate divided by number of compounding per year, to the power of total number of compounding in the entire period, minus 1 over, now this 1 cancels that one, and you get r over n. So this P is going to be the payment, and whatever comes out of this, instead of being called A, is the future value of your annuity, the money that's going to be accumulated in that particular account. So we saw an example of application of a problem that you see in your Algebra 1 and Algebra 2 class under concept of product of sum and difference. So this is sometimes referred to as product of sum is going to be this one, and difference is, well, here you are taking this difference of these two, so it's got the difference. We can extend this thing to various powers. Just patiently do the multiplication. We see that in every case there is a simplification. The formula generalizes for any exponent. Here we wrote it all the way up to power 4, but you can write it for any power. In the problem that we had started with, the highest exponent was 19. That would be 20 total periods minus 1. And then, same shortcut applies, that increase the exponent by 1 and divide by x minus 1. We say this idea applies to interest rate calculations because every time you're doing compounding for one less period than the previous one, and we add all of these things in the annuity, and the total is going to be extracted from an application of geometric series. So I just wanted to mention that there is a basis for the formula that we are presenting here. If you are interested in this type of calculations, you want to take a course in calculus and perhaps look in the direction of econometrics and issues of that time. Okay, until next time, good luck and God bless.